Hi all. Today we are going to study a new topic, that is Lagrange multiplier. Using the Lagrange multiplier, we have to find out the maxima and minima. Before that, this was a conclusion in the last class. Using the second derivative test, how to find out the absolute maxima and absolute minima. Right? For that, find boundary points and critical points. And at these points, using second derivative test, find out all these conditions in the second derivative test at each point of this boundary point and critical point. Okay, that is fxx and its determinant. If xxx is less than 0 and the determinant is greater than, if the determinant is greater than 0, then we can say that the function has local maxima, local minima exist. If the determinant is less than 0, then the function has saddle point. Okay, and if the determinant is greater than 0 and fxx is less than 0, the function has local maxima, and if it is greater than 0, the function has minimum point. This was the conclusion in the last class. Okay, so next I'd like to explain about the constraint maxima and minima. The constraint maxima and minima. So using an example, we can explain these. The first question is, find the points P of x, y, z closest to the origin on the plane 2x plus y minus z 5 equal to 0. 2x plus y minus z minus 5 equal to 0. Find the point P closest to the origin. Find point P closest to the origin means, suppose this is a point P origin. Suppose this is a point O. Then OP, this is a equal to OP equal to what? Root of x minus 0 whole square plus y minus 0 whole square plus z minus 0 whole square. That's equal to square root of x square plus y square plus z square, subject to the constraint, the given question 2x plus y minus z minus 5 equal to 0. Okay, so this is the OP. This is the distance from the origin to the point, right? And in that plane, the plane is 2x plus y minus z minus 5 equal to 0. This is a plane. In this plane, we have to find out the point at which the OP is minimum. Closest to the origin means this distance must be very minimum. Okay, so I'm substituting the function as f of x, y, z is equal to, I'm not considering this square root, I'm considering this function as, we have to minimize this distance. So that means we have to minimize this function. In order to minimize the square root of this function, we only need to take the function x square plus y square plus z square. So I am considering this f of x, y, z equal to x square plus y square plus z square. Okay, so our problem is converted into this type. That is, minimize this f of x, y, z. Minimize f of x, y, z equal to x square plus y square plus z square, subject to 2x plus y minus z minus 5 equal to 0. This is our question. Okay, so we have to minimize this function subject to this function. So from this function I can write this as z equal to, this is actually a 3 variable. We have only studied about the 2 variable function in this. So z equal to, I am converting this, z is equal to 2x plus y minus z. Okay, this is our first equation and this is our second equation. Okay, so convert the 2, substitute 2 in, no, sorry, this is 3, substitute 3 in 1. Therefore, f of xy z equal to x square plus y square plus 2x plus y minus 5 whole square. Then what happened to this function f here? X square plus y square plus 2x plus y minus 5 whole square. And this function f is, the function is 3 variable. This function is 2 variable. So we converted the function of 3 variable into 2 variable. Okay, we converted this function from 3 variable into 2 variable. So what was that function? F of xy equal to x square plus y square, not f of xy. This is h of some xy plus 2x plus y minus 5 whole square. So what will be hx? What will be hx? hx equal to 2x plus 2 into 2x plus y minus 5 into 2. This equal to 2x plus, that is 8x plus 4y minus 20. That's equal to 10x plus 4y minus 20. And what will be hy? hy equal to 2y plus 2 into 2x plus y minus 5 into 1. This equal to 2y plus 4x plus 2y minus 10. This equal to 4x plus 4y minus 10. So in order to find out the critical points, first we have to substitute hx equal to 0 and hy equal to 0, which implies x plus 4y minus 20 equal to 0 and 4x plus 4y minus 10 equal to 0. Okay, subtract this, then 6x equal to, this will be positive sign in this, 10. So x equal to 10 by 6 equal to 5 by 3. Similarly, by substituting this, we will get y equal to 5 by 6. Okay, this is a critical point in this. Okay, so next evaluate this point at which this happens. This function will have the minimum value. Okay, value at hx at these critical points. Okay, so then what will be said here? Z equal to 2 into 5 by 3 plus 5 by 6 minus 5. It's equal to minus 5 by 6. So the point is equal to 5 by 3, 5 by 6 and minus 5 by 6. This is the point. Okay. So at this point we have to check whether this becomes, what will be hxx become maximum or minimum. Hxx equal to, actually this is 10, which is greater than 0. And also we can see that this determinant is greater than 0 by using the second derivative test. By using second derivative test, we can say that this determinant is greater than 0. So at 5 by 3, 5 by 6, h has minimum value. Now at this point, we have z equal to minus 5 by 6. Okay, so the point 5 by 3, 5 by 6 minus 5 by 6 is the point at which the function have minimum distance from origin to that point. Okay, this is a problem in that. Okay, the same problem we can do using the method, that is the Lagrange multiplier method. Lagrange multiplier method. The method we can explain using this. The problem is our problem is find extreme values. Find extreme values of a function f of x, y, z, whose variables are subject to a constraint g of x, y, z equal to 0 are to be found on the surface g equal to 0 at the points where del f equal to lambda into del g happens for some scalar lambda, and this lambda is called Lagrange multiplier. This lambda is called Lagrange multiplier. Okay, so this is a method of Lagrange multiplier. First, given f and g, we have to find. We have consider this equation del f equal to lambda del g. Solve this equation and find this lambda. Okay, then you will get this lambda is called the Lagrange multiplier. Then using this lambda, you can find out the point at which the function is minimum or maximum. Okay, subject to the condition g of x, y, z equal to 0. We can do the problems in the next class. Okay, thank you.